So maybe okay. I can introduce a bit myself. I'm a faculty member of computer science department. Some of you have known me. I basically work on the area of software engineering. The other thing is, okay, you can ask me questions with software engineering, or maybe I ask you some questions. Okay, why? Okay, do you have any expectations with software engineering? Or do you know what software engineering is? No? Oh. So that's why you take this course. Right. Software engineering is tries to apply discipline to the production of software. All right? Like mechanical engineer. When we are a mechanical engineer, when we want to build a piece, a work piece, we want to apply some mechanical engineering disciplines. Now, people think about what if software? Do we have any engineering disciplines when we build software? So that we can build software to the highest quality. I believe you have a lot of experience to always apply patches to Windows or to any application software, right? We need to apply patches almost every month. Why? Because there are problems with software. Okay. So software engineering is very simple, applying discipline to the construction of software. All right? Now, nowadays we have a lot of technologies. So some of you have already learned Java, right? Okay. And we also have things like EJB, Enterprise Java Beans. And we have things like Sharks. We have things like Spring. We have Hibernate. We have Ant. We have WSDL.
要shut down 再着火先。
哦，shut down。
係，等一陣先。
OK，
你繼續講先。
好。Right. So we have a lot of technologies. Now, we may ask ourselves, why do we need so many technologies? We find release of new technologies every week, right? If you pick up, very easy. If you visit the Apache, have you heard about Apache? Yes. Apache. If you visit the Apache web pages, each week you find Apache launch some new project and release new technologies to help us how to build software in future. Okay. Now the question is, where are we? In fact, it is very simple. All our development regarding applying discipline to building software just to solve a single problem. And this problem is what we call complexity. And we address these complexity problems by introducing a discipline in software development. Okay, thank you. Okay. Right. So let me give you some example. Originally, we have assembly programming language, right? Assembly programming language. Many years ago, we have assembly programming language. Using assembly programming language, we can write very flexible software. We can write software which can modify itself during runtime. Do you agree? Okay. We can optimize every details of our piece of software. However, after a while, we find assembly language alone cannot cope with the complexity or the requirements of our applications. So people proposed the use of high-level language, such as Fortran, COBOL, Pascal, and so on, right? So we have this. Now, the emergency of this high-level language is to try to address the complexity problems at those days. And the way to address the complexity at those days is to introduce additional disciplines in writing software. So, could anyone tell me what is a discipline introduced by high-level language, such as Fortran, or Pascal, or C? Okay, some of you might also have also learned C before. What's a major discipline introduced by those language? Not object-oriented, not yet. For example, we don't have the concept of class in C. We don't have the concept of inheritance in Pascal. A very important discipline which affects how we develop programs these days. Sorry, we are with readability. Yeah, so readability, yeah, not discipline. By disciplines, I mean something that restrict how we write program, constrain how we write program. So what's this? Constrain how we write programs. A very important thing, it is introduce a type system. A type system. In assembly programming language, we don't have the concept of real number, integer, string, right? But we do have, okay, this kind of type system in high-level language. And when we write our programs must conform to the type system as specified by language. Otherwise, we get errors. And because of that, we have what we call the compilation phase. Right? Compilation. Before we have high-level language, we don't have the notion of compilation. When we write just assembly program language, assembly programs, we can run it immediately. We don't need to compile it. Right? Now, because of the type system, we are able to identify a lot of errors before we run our programs. Do you agree? And this also affects how we do programming nowadays. We need to compile it because the programs nowadays still fall within the type system, programming language. Now, obviously, type system constrain how we develop software, because we cannot arbitrarily assign a string to an integer, right? Okay. After that, people find inadequacy of high-level language and introduce structural programming. Introduce structural programming. So what is the discipline introduced by structural programming? Have you heard about structured programming before? Structured programming. A structured programming is a programming style without using GoTo. Without using GoTo, right? Do you remember? So structured programming imposes a discipline where each programming block must consist of single entry and single exits. Right? We have to write a program by means of block with single entry and single exit. This is a constraint. Right? And that's why our while loop, our for loop, our switch case, our if then else statements have single entry and single exit. In Fortran and COBOL, and even in Pascal, we can use GoTo, arbitrary. And after that, we have abstract data type, ADT, which further confine us to put data and operations upon this data together. Right? Discipline. And we have OO, as suggested by your classmates, where we need to force a discipline of encapsulation. Right? We need to put down the methods, whether this is private methods, whether this is public methods, we need to hide implementation details as far as possible by using public, private, protected, and so on. When we come to, even higher complexities, let's say building software on top of the internet or World Wide Web, people proposed the use of Java. Java actually was originally developed for programs over internet. All right. So we look at Java. If we, let's say, want to write a Java applet, we are not even allowed to define our main routine. Have you seen any main routine in a Java applet program? No. We are not allowed to do so. We have to define the operations under several methods. The init method, the start method, the stop method. Right? We need to put down what this applet is supposed to do. When the applet is init once, at the web browser, and then put down, what this applet is supposed to do when the browser start the execution of this applet, and to put down what this applet need to do when the user switch to another page, when this applet becomes inactive. When we write a Java multi-threading, because we need to deal with multi-threading, let's say we use Java to build a GUI, graphical user interface. Very likely, this graphical user interface needs to support multi-threading, because concurrent activities could happen, right? If we need to program Java threading, we have to put down what this thread need to do under a method called run. A run, R-U-N. However, we are not allowed to call this run method ourselves. We have to call a method called start. And in the later, if you learn EJB, the enterprise Java bins, we are even required to divide the interface of a bin into what we call a home interface, a remote interface. We put down the life cycles, how to manage the life cycles of bins under a home interface. And what business methods supported by these bins under an interface called remote method. We are also asked to divide our bins into session bins, entity bins, or message-driven bins, depending on the responsibilities of these bins. Even for entity bins, we also need to define whether this bin is a bin managed or container managed. Right. Yet, we find more and more disciplines constraining how we write programs. By doing so, we can leverage the built-in support of the middleware of the underlying layers. And we are able to write more complex programs. All right? So, the idea of software technology development is basically to identify complexities we encountered at this stage. And then people try to define new disciplines through these new technologies to address the emerging complexities. Still follow? So to come back to what you learned in object-oriented design. In old days, we don't have the notion of object-oriented design. It's easy. What we need to do is we have high-level requirements, and then at most we break the high-level requirement into smaller requirements, and then we implement it. It's very flexible. Yet, it cannot meet the complexities of requirement these days. Well, for example, you are asked to document the relations between entities using class diagrams. Right? You are asked to document how the application is going to be used using what we call a use case diagrams. You are asked to put down the inner algorithm or mechanics of the objects using what we call state diagrams. By doing so, we can capture different perspectives of a piece of software. Right? So software nowadays are very complicated. So go back to the slides we visited last time. We have a customer. Customer is a more general concept. We can be refined into buyers and seller, and the notation is UML is a triangle like this. With this inheritance relation, we can put down the constraint of this relation. For example, whether there are some overlapping in between the buyers and seller, or whether customer must be buyer and seller and nothing else, and so on. So what's the coverage? What's the coverage of auction and regular and reserve? So auction can be a regular option, can be a reserve option, auction. However, auction could also be some auction. Let's say as a French auction, an English auction, which are beyond regular and reserve. All right. However, when we try to bid something, we have to stay with a particular auction. So this one is disjoint and incomplete. All right. Stereotype. Stereotypes allows us to refine and UML object concept. In this example, we have classes. So pen tracker, order form, bank accounts are all classes. By putting stereotypes here, control, boundary, and entities, we want to say that pen tracker implements some business logic. Right? So it is a control object, it's a controller, which is responsible to realize the predefined business logic of a requirement. And then we have order form to be a boundary class. So we expect this order form need to interact with our users. And we have bank account entity. So bank account is the entity which means information stored by this bank account must be persistent. It can survive system failure. Alright? The boundary class, control classes need not survive system failure. By putting entity by refining bank accounts to be entity class, which means that we store important information. Links prescribe the relations between objects. So here, we have different objects. James Cock, Degli, Professor Gu, Frank, Pendrew, are different instances of person, and we have different organizations and different classes. Now we can use link to put down the relations between these instances. Let's say we have a works for relation, and we can put down Brad Lofczewski works for HKUST, and he teaches Comp211. We can also put that Fred also teaches another course 332. So as a result, we can use links to relate object instances. Now based on these object instances, we can derive association. So we have the association teaches between person and cause. This teaches association reflect these links. Copy these links. Alright. So we have person and cause. And these two domains, these two sets are related using a relation called teachers. And in UML class diagram terminology, we call it association. So association class diagram is a static element. In this diagram, we simply want to put down a person can relate to a cause using a relation called teachers. but we have not specified, okay, which person teaches which course. All right. When we put an application to run, like this one, okay, when it comes to the real life scenario, then we instantiate our association into links. So here we have 5 different links linking, okay, 5 different persons to 5 different courses. Sorry, to 4 different courses. All right? Do you follow? This is what we call the object diagram. We call the relation and these object diagrams, which is created when we put the system on live as links, and we put down, okay, the relation between, okay, the sets where we have not elaborated on a particular instances as association. All right. So in terms of C++, in terms of programming, person and courses are classes. When we write programs, when we put down, okay, a class called person, we have not defined, okay, this person must be Peter or this person must be John. John and Peter only comes into existence when we run our program. Do you agree? All right. So, in programming, this basically are 2 classes. And what's this association? This association could just be, okay, we have a field in the person, all right, that can bind to an object, a course object. Do you follow? In other words, before implementation, we try to capture relations, okay, between concepts. In this example, we have 2 concepts, person and course. All right. In our implementation, these 2 concepts could be implemented using a C++ class.
Can we say there is a field in course which relate to one object or person?
A field in
there is a field in course.
there's a field
and it's related to the person, the object, person object.
Yeah. Yeah. We can, yes, you're right. We can consider there must be some, okay, tracking between, okay, a person object and a course object. But in this diagram, I have not yet specified whether, okay, I will put the field under person or put the field under course. All right. I haven't elaborated that. It's just, okay, at the design level, I know that there must be some tracing between a person and a course. Right? Exactly how this can be implemented will be an implementation details to be considered later when I have my design ready. Okay? I just try to give you some, okay, illustration. Okay. So at runtime, suppose I have, okay, a person class and a course class. At runtime, I will create, okay, here I will create 5 different objects based on the person class and create 4 different objects based on the course class. All right. Okay. For each of these objects, I can put an identifier. Okay. So these have an object identifier of James course, the other has identifier degree, and so on. And then depending on my implementation, if I have a field, okay, from course to person, then I would instantiate this field. Let's say, okay, Comp211 will point to this object. All right, or vice versa. If I later on, if I decide to put a field here at the person rather than at the cause. So I will have a field at the person object, okay, pointing to the Comp211 object. Do you follow? So this object diagram is a one-time concept. It's a one-time artifact. This artifact does not exist until we run our application. Right? Okay? Association is a static concept which should exist, okay, at compilation time. This is how we write our program. Okay? When we write our programs like this program and this execution can capture this relation in our real life world. So in our real world. Okay. Any questions? So I hope you can understand the difference between links and association. Okay, this is what we call association. Okay. We use association to link two classes. So I say to relate. We use association to relate two classes, and we use links to relate two objects. Okay. Okay. Similarly, we also have another two classes: person, as organization, and association works for. Okay. Now, what does it mean? It means something like this. Now suppose I'm going to build a system, and I know that this system should be able to support this information. All right, should be able to store this information. Then, okay, in my programs, I should have these two class diagrams. All right. So we relate the two persons, and then we can join these two association, teachers and works for. The arrow here indicates navigability. What's navigability? Navigability means we should go from person to cause, but not vice versa. All right. So if I put an arrow here, which means I more or less have decided to put a field under the person class pointing to a cause object. All right. Okay. If we, like this, have not specified any navigability, it means that we have not made any decision, or they can both, it can go both ways. There can be several associations between two classes, like attended and works for. So we have James Cook attended HKUST and works for you HKUST. All right. So this is the object diagram. This is the class diagram. We implement class diagram where we write our programs. And when this program is run, we got the object diagram. We can have recursive association. Sorry, unary We have unary association. This is what we call unary association, which means person married to person and person manages person. Now, if we put unary associations like that, we can have Mary married to Tom. It's just Mary is a person and Tom is also a person. So we put down person married to person. And similarly, person manages person. We can have John manages Tom. Both Tom and John are persons. Alright? This is what we call unary association. So unary association is reflexive by itself. It relates a class to itself. A binary associations is an associations relating to classes. And we can also have ternary associations that relates more than two classes. In general, we have n-ray association that have an associations relates multiple classes. In practice, most of the time we use either the unary associations or binary associations. Now, having put down the relations between classes, we also need to put down the multiplicity. For example, we want to put down how many courses does a given instructor teach. Alright? An instructor does not have to teach any course, but may teach more than one course in a given semester. And so we put down 0 dot dot asterisk here, which means an instructor teaches 0 course at least, or an instructor teaches many courses. You follow? The meaning of this multiplicity, read this in this way. An instructor teaches 0 course, an instructor at most teach on multiple courses.
So should we put an arrow here because it's from instructor to course?
Not necessary, because we can have course back to instructors. For example, can a course be co-taught by multiple instructors? Alright? If it's the case, we'll put the star here. Or, a course must have at least one instructor. If it's the case, we put 1 dot dot star. Do you follow? If a course must at least be taught by one instructor, we put 1 here. And a course, let's say, can be taught by multiple instructors, put star here. Right. So the decision between multiplicity and navigability are orthogonal, independent. All right? So this basically, we try to use class diagram to capture real-world constraints. However, in this class diagram, I have not elaborated whether John and Peter will co-teach a course or not. All right? Or how many courses will be taught by Peter? Such information could have been found in this class diagram. In this class diagram, I have just captured real-world constraints. That a runtime system, that's the system and this runtime must obey. Do you follow? I just put down constraints and disciplines that this system and this runtime must follow. This is just a note for 231 students. Okay, ER model and UML models represent data requirements similarly, although UML model later on you will learn how to use UML models to represent active elements, not just data. However, placement of multiplicity ER models used in 231 may not be compatible with that of UML. So, this one makes up ER and UML. In general, the syntax of multiplicity is this one: A dot dot B, C dot dot D. Okay. The minimum number of links in which each object can participate in associate A, will be put down in here. Okay. So we have 0. 0 means optional. Bean card C1A. Equal 0 means it's optional. If it's greater than 0 means it's mandatory, like in our previous example. A star means an unlimited number. Mean card equal 1 and max card equal 1 means 1 and only 1. A mean card equals 0 and max card equal many can be safely replaced by many. So here comes more examples. So in this example, we want to capture information of this scenario. So what should we put down as multiplicity in country and city? So we want to say that a country, what should we put down here? A country must have one and only one capital city. Right? And and a city, given a city, it can be a capital of at most one country. For example, Hong Kong is a city, but Hong Kong is not a capital of any country. All right. Beijing is a city, but Beijing is a capital of China. Okay. A city can be a capital of at most one country. For this reason, we put down 0.1. All right. Do you follow? 0 means can be none. 1 means at most 1. Okay. Assignment here. Employee assigned to department. So this is a class diagram. We want to abstract the real life constraints to this class diagram. So how are we going to do so? In this diagram, we find that we can have multiple employees in the same department. All right. So how are we going to capture multiple employees to a single department? And also find that, okay, an employee can be assigned to, okay, one department, only one department. Okay, some department, okay, may not have employees assigned to it, right? So, to capture that each employee must be assigned to one and only one department, we put down 1.1. Right? An employee assigned to at least one department. An employee assigned to at most one department. So, and that's why we have one and only one. And as a result, we can simplify 1.1 to 1. We have, okay, department, like production, does not have any employee. And for this reason, we put down 0. Right? However, there are departments contains multiple employees. We put down star. Do you have any question about putting down and understand multiplicity in an association? Okay. How about this? In this example, we have the relation between supplies and parts. Now we know that a supplier can supply multiple parts, and some parts can be supplied by multiple suppliers. We can have some parts not supplied by any supplier. For example, these are the parts that made by ourselves. And we can also have, some supplier do not supply any parts. Okay? So to capture the constraint that a supplier can supply multiple parts, such as e-com and high-tech, we put down star at the end part of parts. Right? We put down the star here at the part end. And if you want to put down a part can be supplied by multiple suppliers, such as 28175. We use the star at the supply end. Do you have any question about this? Remember, star means 0 dot dot star. Star is the same as 0 dot dot star. Question. Now I want to represent the constraint that a student must enroll in at least one course and can enroll in at most 5 courses. What do we have? At least one. 1 and at most 5. So 1 dot dot 5. All right? A course must have at least 10 students enrolled in it and cannot have more than 45 students enrolled. So we have 10 dot dot 45. Is it clear? So these are the multiplicities that one would deduce from the above statements. But however, okay, it's a bit tricky in the sense that, okay, when we start our enrollment system, we might not have, okay, any students enrolled in any course, right? So what is the most likely multiplicity of following associations? Customer mix bid. So we have one and only one customer, okay, mix bid. Okay. So given a bid, it identifies a customer. And a customer can mix multiple bids. Can you read it? And okay, customer posts item. Again, we have, okay, a customer can post multiple items, but an item is only posted by one customer. A bid is for one item, and we can have multiple bids for the same item. Okay, in an auction, we can have multiple bids bidding an item. Okay. However, given a bid, it must identify an item. Okay. Purchase. So we have multiple customers purchases multiple items. Do you have any questions before we move on to this one? So here, I extend the first class diagram a little bit. We have, okay, students as a class of customer. So student is a customer, all right? Okay? And a customer can multiple bid. So what's the multiplicity between, okay, student and bid? Okay, according to this diagram, how many bids can a student, okay, make? Many. So for a bid that's, okay, made by some students, okay, how many students would this bit identify? For students bit, how many students would this bit identify? According to this diagram. 1. Do you follow? So the relation between customer and bid, it is inherited by the students.
But the question is, only student and customer. Is there other customer other than student?
Yes, it's possible. So this inheritance is,
Which means not each bit is bid by one student, because there's other possibility other than student, right?
that's true. Okay. Let's say that a bit identifies a customer, and that's why in my previous question is for a bit that made by students. How many students with this bit identified? Right. Okay. Any question? Multiplicity. Okay. So here comes the multiplicity of n-ray association. So how are we going to interpret multiplicity of n-ray association? When we determine the multiplicity at the Cn, we basically want to specify how many C objects may appear in association with a particular pair of AB. All right. Let's take an example. Suppose we have a general association registration relating course, student, and professor. And we want to capture such a requirement that a student will not take the same course from more than one professor, and a student may take more than one course from one professor, and a professor may teach more than one course. So how are we going to put these constraints using multiplicities? Now let's take a look of the multiplicity at professor level. According to this semantics, when we determine the multiplicity of professor, we are determining the number of professor associated with a course-student pair, right? A course-student pair. So for each course-student pair, we have 0 or 1 professor. A student will not take the same course for more than one professor. Right? This constraint is translated to, for each course-student pair can be at most one professor. Okay? Do you follow? For each student professor, we want to fix student and professor, which means we are determining the multiplicity of course. For each student professor, it can relate to many courses. Each student professor pairs can relate to many courses. Because a student may take more than one course, and a professor may teach more than one course, right? For this reason, we put down a star at the course end. For each professor course, you can have many students. All right? Do you follow? And that's why we put a star at the student end. So do you see how we put or formulate real-world constraints using class diagrams? This class diagram, I think you might also believe, agree with me, is clearer than this expression. It's easier to read and understand than this expression. All right? Okay. Now imagine if we have a relation, any relation relating, let's say, 10 concepts. I'm not sure if you can put it down in English. Okay? Okay, I give you a homework. Okay, try to model the politician, in Hong Kong, and their political parties, and and the relationship, and also the relationship with legislators. 可唔可以啊？可唔可以做啊？政客佢嘅政黨 ，OK， 同埋佢有冇參加呢個直選，同埋佢入到呢個立法會。There must be some constraint, right? 仲有一個叫名單，係啊，仲有一個名單，漏咗啲有個名單。因為如果佢唔喺名單嗰度，佢就冇辦法被選到噶嘛。但係佢喺名單裏邊，佢唔一定會被選到嘛。啱唔啱啊？Okay. Now, let's try, another example to drill, to get more drilling on ternary association. We have course, classroom, and day, right? So when we put down, when we put down the day, for each course, classroom, 0, 1, 2, or 3 days a week, all right? And here, we want to put down, a classroom given a day may serve 0 or many courses. And given a course on a particular day, it may occupy 0 classrooms. Any questions so far? Role names. Role names, okay, specify the responsibilities of a concept in an association. So in the association works for, a person plays the role of employee while company plays the role of employer. Role names can be used to navigate an association. In particular, we put down role names for unitary association. In this example, we have person, managers, person. And we put down the role names, boss and workers at two different ends. Now, based on the role names, it's clear that we goes from boss to worker. Alright? 除咗啲特別嘅公司之外，okay. In general, okay. A person who plays the roles of boss, managers, person who plays the role of workers. Right? Do you follow? For unitary association in particular, okay, we need to put down the role names because otherwise we don't know who manages who. Okay. Any question? Association class. In some relation, okay, we need to put down certain attributes, such as, we want to say that Marco got A plus in course 332, got B plus in course 201, and got A minus in course 303. Now the question is, where do we keep these attributes? Should we keep the attributes, this information, A plus B plus A minus, under the class student, or should we keep them under the class course? Where should we keep it? Note that the case could be complicated by many students taking the same course. So the first possibility is to keep attributes under grade. Sirs, okay, you keep the attributes, the grade attributes under students. What's the problem? If we keep grades, the grade attributes under students, what's the problem? Cannot
search the student grade of the course.
Okay, which means it's not clear which grades belongs to which course, right? And also it's not clear how many grade attributes should be prepared in advance. Okay. How many grade attributes do we need? And how to identify a grade for a course? Another alternative is to keep the grade information under course. What is the disadvantage?
We don't know what grade the student got.
Yeah. So we cannot identify, okay, which student got this grade, right? And also, we are not sure how many grades we need to prepare in advance. Because a course could be registered by 10 students, or some course could be registered by 400 students. So how many grade attributes should we prepare in advance? It's difficult, right? So let's imagine if you are asked to implement, okay, a class like this, you will need to use dynamic data structures. And if you are asked, okay, to keep this under a table, it will be a problem. If this to be kept in a table, we are not sure how many columns we need to prepare in advance to store the grades. Do you agree? All right? Another possibility is, okay, use a multi-valued attribute. Okay, again, okay, as pointed by your classmates, okay, it doesn't solve the problem. It probably solves the storage problem, but cannot solve the problems, okay, how to identify a grade for a course. And again, okay, if we use the multi-value attributes, it can only solve the storage problems, but still cannot solve the problems to which students does a grade apply. So the solution in UML is to have the association represented in a class. So the association itself can also be a class in UML. So this is a class, the association itself is a class that can hold its own attributes. So with this class diagram, we can instantiate object diagrams like this. We can have, okay, Marco links to 52, all right? And the attributes grades set to A+. We can have Marco links to 201, okay? And the attributes of this link is B+, and so on. Okay? Do you follow? Okay. 完㗎啦。Okay? So let's stop here. And okay, Professor Gu will continue next time. Thank you.